Hello, we are Team 7. Today we are presenting bridging the gap between soft RL and generative neural networks. Here is the table of contents. We begin by addressing the challenges associated with GFlow nets. GFlow nets function as a trained stochastic policy or generative model, sampling objects in proportion to reward function through a sequence of constructive steps. This sampling process closely aligns with reinforcement learning methodologies. In our project, we aim to broaden the application of RL principles to GFlow nets. Previous research primarily explored the learning of GFlow nets as an entropy regularized RL. But this was restricted to scenarios with a tree structure or when the temperature parameter is set to 1. To address this, we extend the theoretical framework to more general cases by reformulating the correlation between soft RL and GFlow nets, emphasizing the role of regularization parameters in enhancing policy exploration. Furthermore, we incorporate advanced soft RL techniques, such as past consensus learning, PCL, and multi-step PCL, into the GFlow net framework, significantly mitigating issues related to bootstrapping and instability. Let's shortly introduce the necessary background. Let's consider a finite discrete space X with a reward function Rx, where our aim is to train a model to sample objects from X based on a probability distribution proportional to the reward function, rather than simply maximizing it. To achieve this, our model must satisfy the flow matching constraint. There are various forms of the objective function, such as detailed balance, trajectory balance, and sub-trajectory balance that are used to address this constraint. The GFlow generation process involves starting with an empty state, progressively adding the new components at each step, as illustrated in the image. Once the flow functions are learned, these enable calculation of probabilities of selecting a subsequent state, ultimately determining the sampling probability of the reward function. In contrast to traditional methods, where a value function is maximized, in entropy regularized RL, the value indicates an additional term for Shannon entropy. Here, lambda acts as a regularization coefficient, as detailed also in the Soft-Bellman equations.
Coming to our contributions, we firstly explore the effect of lambda. We note that using larger values of lambda biases the agent towards less deterministic policies, a phenomenon known as stochastic bias. Reducing lambda can diminish this bias, but this adjustment comes at the cost of decreased exploration, increased training instability, and less robustness to changes in the environment. Consequently, we argue that in training scenarios of GFlow nets, a single fixed lambda value captures the advantages of soft RL. From this insight, we propose an equivalence theorem which bridges GFlow nets and soft RL by setting specific reward values. It expands the established correlations beyond just lambda equals 1 to include any non-negative values of lambda. As our initial strategy, we've introduced an off-policy deep RL algorithm that treats lambda as a random variable. By integrating a range of lambda values, we avoid the limitations of fixing lambda. For stability, all networks are conditions on lambda, as outlined in the provided steps and pseudocode. Secondly, we assume an inverse relationship between rewards and exploration. Early insufficient sampling leads to low reward expectations, resulting in a uniform action distribution to encourage exploration. As sampling increases and reward expectations rise, the value of lambda should decrease, aligning more with exploitation strategies. Therefore, we model lambda as a learnable function dependent on the state action values. Next, we introduce the integration of advanced soft DQN strategies into GFlow net training. We have implemented training using soft DQN with GFlow net rewards. Traditional DQN faces a bootstrapping problem because it uses the learned Q function as a target for regression, leading to instability and slow gradient updates. To address these issues, we employ unified path consistency learning, PCL, which updates Q values for all actions from a state simultaneously. While PCL increases efficiency, the bootstrapping problem is not entirely solved, as the value function still relies on bootstrap values from the next state. To further refine this, we integrate multi-step PCL that maintains consistency across steps. The target network parameters, theta bars, are driven solely by rewards and log policy, as you can see from the equation. Coming to the experimental results, we start with a synthetic hypergrid environment. You can pause the video to read about the environment description. In the synthetic hypergrid environment, we assess GFlow net's performance by measuring the L1 distance and KL divergence between the true and empirical reward distributions. In a hypergrid with a site length of 20, learnable lambda DQN converges faster than other algorithms, including soft DQN, Bayes-Lines, Munchausen DQN, and soft DQN. Normal and uniform lambda algorithms show rapid convergence, whereas gamma lambda converges more slowly. Multi-step PCL DQN and PCL DQN exhibit convergence patterns similar to GFlow net's baselines of trajectory balance and detailed balance. In a more challenging hypergrid of the same size, learnable lambda DQN still leads in convergence. Normal, uniform, and gamma lambda DQN show similar patterns to a simpler environment, but multi-step PCL DQN and trajectory balance fail to converge. Increasing the site length to 32, learnable lambda DQN remains the fastest. Normal and uniform lambda algorithms display similar convergence rates, while gamma lambda DQN lags. PCL DQN and detailed balance converge at comparable rates to the soft RL baselines, with multi-step PCL DQN converging noticeably faster than trajectory balance. In the more difficult 32-length hypergrid, most algorithms show similar trends to the standard environment. However, uniform lambda DQN slightly outpaces normal lambda DQN. Both multi-step PCL DQN and trajectory balance do not converge. Additionally, we conducted experiments on bit sequence generation with a fixed length of 120. Evaluation using Spearman correlation and the number of modes captured reveals learnable lambda DQN again as a top performer, closely approaching the maximum value of 60 faster than others. Gamma lambda DQN also performs notably better in this task compared to others, as opposed to earlier tests. In addition, Table 1 shows that reward correlations across all algorithms are similar, with baseline, Munchausen DQN showing slightly superior performance. In conclusion, you found that learnable lambda DQN generally leads to faster results. While normal distributions often perform best for sampling lambda, no single distribution is universally optimal. Effectiveness varies by task. Additionally, the similar performance of PCL with detailed balance and multi-step PCL with trajectory balance across experiments can be attributed to their objective similarities, which are influenced by Monte Carlo and temporal difference methods in RL. Further theoretical analysis of this relationship is planned for future work. Finally, we see substantial potential in expanding the integration of RL into generative flow networks as a promising research direction. Thank you for listening.